Okay, yeah, now should be working. Okay, yeah, hi. As I mentioned on Monday, Linda is not here today. She is busy with the applications of the new professors, so she asked me to step in. I decided on talking about elliptic curves over C, as we have avoided this part so far, so we were mostly concerned with rational points on elliptic curves in essence, but the theory of elliptic curves over C is particularly interesting because you have access to the whole theory of holomorphic and meromorphic function, which somewhat changes the flavor of the theory of elliptic curves over C. Okay, and to make this a bit more precise, what I want to do today is to prove something called the uniformization theory. So for elliptic curves over C. And this, well, I will give a precise statement later on, but the slogan you should keep in mind for this is the following, that over C, elliptic curves are nothing else than tori. So you can identify every elliptic curve one-to-one in some sense with a torus, and we are going to prove this. Yeah. Exactly. Anything else I wanted to mention here? No. Yeah, as I mentioned already, we will be doing this through the usage of something called elliptic functions, and also a bit of modular functions. These are just particular kind of meromorphic and holomorphic functions which satisfy a lot of symmetry conditions on the complex plane. And the plan now will be first, to, well, explain exactly, in some sense, what a torus is. More precisely, we will be dealing with lattices. So torus is just the complex plane modular lattice. So lattice is something that looks like this, and taking C modulo this identifies these two sides with one another, so you basically get a torus. And so what we refer to is how we can define to a lattice an elliptic curve, and then show that this assignment is, well, bijective in some senses. Bijective modulo sum relations is bijective. I would just put it like this. Okay. I apologize in advance. This is an I. These are I's. People are often confused with this. Yes, I'm looking at you, Skylar. But yeah, so please keep that in mind and ask if some notation becomes unclear. I tried to do it, but I already failed here. So, okay. So this is the basic plan for today. Depending on the time, I have some stuff prepared for the end of the talk where I can give you some insights why this theorem is useful in the end. Okay. Let's start. So the first definition should be that of a lattice to fix some notation. So a lattice, I sometimes write like this, is just the z-span of two complex numbers not lying on the same line. So a lattice in the end looks, so this is a lattice. Lattice. So this looks something like this. This is the complex plane. You fix two points, omega 1 and omega 2, and you consider all its z multiples. So you get the point here, you get the point here, the point here, and so on. So it is in the end just a lattice, and we call such a thing here a fundamental domain. Fundamental domain, in this case, everything clear, or are there any questions? Okay. Fundamental domain centered at 0. I denote it like this. Because essentially what we want to talk about are functions which are periodic with respect to lattice, meaning their values repeat once we plug in every lattice points. And this basically allows us to reduce anything we want to know about the function, say in this parallelogram to this parallelogram, or from here to here, or basically from any point in the complex plane to such a fundamental domain. We can use any one of these. We can also translate them a bit around, and this will not change anything. And maybe to just keep it for later, we can actually somewhat normalize lattices by something which is called homothetie. Homothetie, awful word to write. Homothetie, two lattices are homothetic, so say you have two lattices lambda and lambda prime are homothetic. If there is some lambda in C star such that one is a multiple of the other, meaning we somewhat rotate one and translate one and scale one of the lattices into the other. And using this we can, and we will assume this at some point, rotate any lattice such that one of its generators is just the unit 1 and the other one is an element of the upper half plane. But I will come back to this later when talking about the J function. Okay, so this just to get it out of the way. And the main object for the first part of this lecture will be that of an elliptic function. So f is elliptic for lattice if it is meromorphic. So we call meromorphic just meaning we have only a discrete set of poles. And so meromorphic on C, meaning it's defined everywhere, and defined everywhere besides the poles, and we have periodicity with respect to the lattice. So meaning we can, exactly what I talked here about in the beginning, we can start in every point in C and basically translate everything back to the fundamental domain. Yes? F is oh yes, sorry. F is meromorphic. Yeah, thank you. Exactly. So these two conditions combined, and we call the order of F is the number of poles in F0, so a fundamental domain, and counted with multiplicity. Okay. So this will be our main object of study. And what we will do is now, I've briefly recall some theorems I proved on Monday in the exercise session. I won't be proving them again, but just stating them here. These are the Liouville theorems. Liouville theorems. Which give you some basic properties of elliptic functions, and those we need the most. Maybe. Whatever. So, first Liouville theorem is that if F is elliptic and holomorphic, meaning no poles on all of C, then F is constant. So there are no interesting double periodic, there are no interesting holomorphic elliptic functions. And the second one is the following: if F is elliptic and we pick a translated fundamental domain so that no poles are on the boundary of this fundamental domain. We need this just to guarantee that we can apply a certain theorem. But again, this does not change anything. We still hit all the relevant values of our elliptic function because they are contained in every fundamental domain, every translated fundamental domain. So all the relevant information of an elliptic function can be seen from any such fundamental domain. I hope it is clear what I mean by this. You just take the interior of So picking linear combinations with scalars between 0 and 1 in both directions. So just to make this completely clear, because I didn't write down a definition. So exactly, yeah. If this holds, then the sum over the residues of f in this fundamental domain is 0. And the third theorem is f elliptic and non-constant in this case. Non-constant. And fa as above, so as in 2. Then the following holds: the number of zeros in fa are equal to the number of poles in fa. Okay. So maybe that gives at least some hints on how to prove this. This is an easy consequence of Liouville's theorem. So the theorem stating that no holomorphic function defined on all of C which is bounded can be non-constant. This here is as you might guess, a consequence of the residue theorem. And this one here combines the part 2 together with the so-called argument principle. The argument principle tells you basically that there is a certain integral which counts poles and zeros. Yeah. Okay. Any questions for that? Okay. Good. So this covers what I want to tell you about general elliptic functions. And from now on, I will only talk about one particular elliptic function, the so-called Weierstrass P function. So let me first define it, then give some remarks on its definition. So for lattice lambda lat, so this will be fun. This is an awful letter to write. Yeah, looks about right. Yeah, so this is sadly its own LaTeX comment, because this is just this is not really a curly P, it's a really awful to write P. But yeah, sorry. This will be always associated to a lattice. I will usually drop this part if it's clear from the context which lattice I'm referring to. And we define this function a bit surprisingly, I would say, at first, the following way. So what we want to accomplish, so, okay, let me first write this down, is the Weierstrass P function. Okay, so maybe to give these sounds are new. To maybe give a brief remark on this definition. So what we want to do is we want to find the simplest possible elliptic function and hope that it suffices for what we need in some sense. And I claim this is the simplest one. So this does not look like the simplest one, but this has a very simple reason. I said the word simple very often. First off, a remark, non-constant elliptic implies order at least 2. This is a consequence of Liouville's second theorem, because consider you have an elliptic function of order 1. This just means you have precisely one pole of order 1 in the fundamental domain. However, then Liouville's second theorem tells you the sum over all the points has to be 0, so the sum of all the points where the function is holomorphic is 0 anyway. So this just tells you, okay, the residue at this one pole has to be 0 as well. This is, of course, only in the stating that this function is actually holomorphic at this point, because the residue is precisely the coefficient which would give you a pole of order 1. So there are no non-constant elliptic functions of order 1, so the smallest possible way you can get is an elliptic function of order 2. Meaning, okay, what we wanted to do is probably place a pole of order 2 in the lattice points. So this would give us somewhat the naive guess to consider this function here. Because, well, we get a pole in every lattice point by construction, and we also get, so if we would know that this function is sufficiently nicely behaved, we would get that this is double periodic, because simply we have chosen our coefficients like this. However, this thing here does not work because it doesn't converge absolutely for any value. So as you can check for the lattice Zi, so the Gaussian integers, this here gives you a non-converging series at 0. So this guess does not work. And what we do in the end by defining the Weierstrass P function is we fix this problem by introducing a convergent summand which somewhat forces the series to converge. So this is why this thing has a bit of an odd form at first sight. Okay, so need to adjust star some not absolutely, and this is star. Yeah, now okay, need to adjust this somehow. And I claim the adjustment is precisely what I wrote there in the definition of the Weierstrass P function. Okay, then let's prove that this thing there above actually satisfies what we need. So meaning, first theorem, first is elliptic of order 2. And to just cover it all at once, what we also need about this function is it satisfies a peculiar differential equation. So this is, by the way, if you look at it, here's a square, here's a cube, here's a linear term. This really much looks like an elliptic curve. And what we are going to prove is that this is actually an elliptic curve. And this will be our way of associating to any lattice an elliptic curve. But let me tell you what these coefficients are. So G2 is 60 times G4 of the lattice. So yeah, I fix a lattice for all of this, as I mentioned. And G3 is 140 of G6. And maybe to get finally an insight what G is. GR here is the so-called Eisenstein series. Omega in 0 lattice points, omega to the R. These are the so-called Eisenstein series. And I will mostly black box their properties here because they are a bit tedious to prove. So yeah, we define these coefficients in general in terms of this series. So to show some properties of these coefficients, it usually suffices to study this function for an arbitrary R. So yeah, it satisfies this differential equation. And the third part is we have a Laurent series around z equal to 0. And this one looks like this. Jesus. 2n plus 1, g 2n plus 2, z to the 2n, with g2n polynomial in g2, g3. And this is independent of lambda. Okay. Exactly. So what I mean by this is we can compute these coefficients, which are precisely these series, in terms of our first two things But this is a general procedure which will be independent of the lattice. This is the important part to note here. This independence then later allows us to give some general arguments that if these coefficients agree, all the higher things have to agree, and so these series have necessarily to agree. This will be a very powerful proof strategy. Okay, so I'm going to prove this. I will first prove part 1, independent of the rest, and then these two somewhat together, because they interact very nicely with one another and somewhat depend on one another. Okay. So, prove. And as I mentioned, I will assume this just as a fact, GR converges absolutely for R bigger than 2. Okay, I will just assume this as a fact. It's not hard to see, but a bit annoying to write down. Okay, so for the first part, what we want basically is want to split up this defining series in, so this part leave it out a bit, into sums and bound the remainder. So we will choose a z large enough so that we can somewhat bound the remainder using this series here. So this is the general strategy. And what we do there is actually we show that on every compact set this remainder converges, and this here is meromorphic, and this gives us by the Weierstrass n test it is in the end that if we can bound all these sums by some absolutely converging stuff, namely these GR, that we get convergence outside the lattice points, and in particular meromorphy then. So maybe to give it a bit more precise, so if Z is smaller than some R, so we choose some closed ball around the origin, then, and we can assume that omega is bigger than 2R for almost all omega and omega. Simply because this is a lattice and at every step we get further away from the origin, and at some point we have to leave the closed ball. Yeah. So this is also the basic fact that the lattice points are a discrete subset of C. So they carry discrete topology, and this is a compact set. And a compact discrete set is necessarily finite. Okay. So these two are satisfied. Then we get that this one is bounded from below. The difference of Z and omega is bounded from below by 1/2 omega. And this further allows us to bound the absolute value of the summons in the Weierstrass P function. Yes. So modulo some computations, you arrive at this by putting these fractions together and using these bounds you already have. And this is the R from above. And note in particular, this here is a tree. So tree is greater than 1. And hence, if we sum over all these points where this condition is satisfied, we get that the remainder tail of the series is bounded by GR. And hence we get that P of X is dominated by G3, hence meromorphic. So yeah, we get that. This, okay, to be a bit more precise, all of this works very well if we work outside the lattice points, so exclude the poles, and then we get that outside the lattice points, this function defines a holomorphic function, and you can check immediately from the definition as a series that in the lattice points it has poles of order 2. So these together then give you that this is a meromorphic function. Okay, so this is, I would say, just standard complex analysis. The more interesting part is the periodicity with respect to the lattice. And there's an interesting remark to be made. It somewhat looks obvious from the definition that this should be double periodic, because if you replace z by z plus omega and rearrange everything a bit, you get the same series back. The problem with this is you would have to split up these summands, 1 over z minus omega squared minus omega squared, 1 over omega squared. And as I mentioned here, these are precisely there to guarantee that the series converges. So you can't just split them up and rearrange them. But you can do this with the derivative of this function, because then you get rid of all these problems. And you still obtain a convergent series because you are in degree 3 or higher, where this problem does not arise. So to maybe put it more explicitly, for periodicity, consider its derivative. And by this argument, something else follows, that we can obtain the series for its derivative just by differentiating summand-wise, because this is all absolutely convergent. And this derivative looks like this, just by computing the derivative of this above. And this is now clearly double periodic, because by the same argument as here, you can bound the summands and to give you absolute convergence. And now you are freely allowed to rearrange these summands, and these summands suffice to see that this function is double periodic. So this still gives you elliptic function, a meromorphic function, which is double periodic. So this actually defines an elliptic function, now of order 3. And now we argue that since the derivative is double periodic, the Weierstrass P function itself has to be double periodic. And let's do this. So so if you now consider the difference of P of z and P of z plus omega, this is necessarily a constant, because differentiating this expression gives you 0 by double periodicity of the derivative. So this has to be constant, and this constant is actually 0, because looking at z equal to, say, minus omega 1 over 2, you get that the value of omega 1 over 2 is the same as the value of minus omega 1 over 2. So this can be seen immediately from the series definition, because all these summands are symmetric in z. So replacing z by minus z, we just swap the negative and positive summands. So negative and positive with respect to z plus minus omega. And this is allowed because we do not have to break apart these summands of the series. So the Weierstrass P function is an even function. And we know that this now is omega 1. Oh, this should be 1. This should also be a 1 over 2 plus c. So what we get is that omega of Weierstrass P function of omega 1/2 is the same as Weierstrass P function omega 1/2 plus c. So we conclude z is 0, so is actually elliptic. The Weierstrass P function is actually elliptic. And as I mentioned, it is of order 2 simply by construction, because we place the pole of order 2 in any lattice point. Okay, that's so far. Any questions regarding this? I take this. Yeah, okay.
What is the notation by S2 with these?
Sorry, that was just as an emphasis. That has no meaning. I just wanted to emphasize this is the part we have to bound, because this is somewhat this is the part where this holds, and this is the remainder. But the remainder is just a rational function, which is obviously meromorphic. So we only have to care about the remainder. Yeah. Thank you. Okay. So far so good. And now for 2 and 3, as I mentioned, we will prove them together in 3 steps. So the first step is to establish that the Weierstrass P function has a lower series of this form. Then to show this form gives us this differential equation, and then finally using this differential equation that the coefficients here are in fact independent of the letters. So for step 1, for z smaller than omega, so if we work with the lattice again, this simply gives us that we want to work within a ball of this radius so that the only pole lies in 0. So because then we know by complex analysis that lower series exists on this annulus, and we now compute it simply by using known lower series. So by definition, the Weierstrass P function is 1 over z squared plus the sum from above, z minus omega squared minus 1 over omega squared. And this term here is just a derivative of a geometric series. So we can use the usual formula for this and plug it in. 1 over z squared plus omega. And yeah, in this geometric series, this will be the first summand. So we get rid of the summand by summing only over n bigger than 1. And n plus 1 omega n plus 2 z to the n. So this is just expanding this here in a geometric series, getting rid of this term, and then putting everything back together. Yeah. And yeah, because this here is absolutely convergent by our argument in part A, we can swap these two sums. Do I want to do this? We can swap these two sums. And what remains then is just g m plus 2 z to the n, because by definition what we get here is the sum over all omega which are not 0 over omega to the n plus 2, or 1 over omega to the n plus 2. This is just the Eisenstein series for n plus 2. And since we know that our function is even, we actually can get rid of all the odd summands and arrive. So did I forget? No, I put it right. Okay, and arrive precisely at the formula we are looking for. Yeah, that sucks. I have to clean the board for the rest of this proof. Here, the order of an elliptic function is the number of its pole, essentially the number of its distinct poles in some sense. So because you know, okay, that was a bad analogy. The number of its poles is the only number we care about of poles, because these are the poles precisely in such a fundamental domain. So we can have poles all over the complex plane, and we will have in fact, but the order is the number which occurs in any fundamental domain with multiplicity. So in our case for this function here, this is of order 2, because in any fundamental domain, well, that's in any fundamental domain, if I don't place this one, okay, that's a bit annoying because I didn't define the fundamental domain explicitly, and now this becomes awful. Let me maybe, yeah, so write this down explicitly here. These are the points t omega 1 plus s omega 2 for ts between 0 and strictly under 1. So this is this part here. And then I want to count the number of poles within this part. So I have one pole here of order 2 and nothing else by construction. So this is also, these points are excluded by construction, and this tells me, okay, in this part here there's one pole of order 2, So counted with multiplicity, we have exactly 2 poles, and this is the order of an elliptic function. Somewhat a measure of how many poles it has. Does this make sense? Okay, perfect. Yeah, we will be almost only dealing with functions of order 2 and 3, which always have just double poles everywhere. Okay, I wanted to clean this board. Okay, my notes. This was step 1, giving us the Laurent series. Now for step 2, using this Laurent series, we can actually show that it has to satisfy this identity. And the first note, again by this compact convergence, we get the Laurent series of the derivative by just taking derivatives of the summand-wise derivative of the series we are given. So this is then of this form. And now note the essential feature. This function here has a pole of order 3 and 0. This function there has a pole of order 2 and 0. So if I take the the square of this function, I get 4 over z3 and some stuff. And if I take the cube of the Weierstrass-P function, I get 1 over 6, and I get 1 over 6 plus something. So by considering this function minus 4 times this function, I get rid completely of this 1 over z to the 6 part. So if I multiply this out, I also get something of degree 1 over z squared, and then I can use just the normal Weierstrass-P function to get rid of this, and then I finally do the same thing with the constant coefficient to match the constant coefficients. So all in all, and we'll just claim this here, if I look at this function, f of z, well, 4 g2 plus g3. This is now arranged in precisely this way, meaning around 0, I have no poles left. I removed the poles of this function by considering these subtractions, and I also got rid of the constant coefficient by adding this part here. So one can write out this in more detail, but I want you to get the essential idea, because this is a very useful concept. So what I now have is, well, I still have an elliptic function. F is still elliptic with respect to the same letters, but at the same time it is holomorphic, because by holomorphic around 0 and then holomorphic everywhere, because I hardwired this in. I constructed this function precisely in such a way to get rid of all the possible poles. And it is, so and f of 0 is 0. So what does this give me? These two parts here give me that this function is constant by Liouville's first theorem, which is still there. That's perfect. So these two give me f is some c, and this gives me c is actually equal to 0. So putting this all together, this tells me I've constructed this function which is holomorphic and elliptic, hence constant and constantly 0. So meaning this function is 0, and then this is precisely the differential equation we are looking for. Okay, shall I go into more detail in this, or are you fine with this explanation? Okay, very good. So and this is, keep something like this in mind. Elliptic functions are very strong with this regard. You can just always consider some differences and such. Maybe this will be on the exercise sheet. Using a similar idea, you can actually show that all elliptic functions of arbitrary order can be expressed as a polynomial in the Weierstrass-P function in its derivative. Precisely by such an argument, by removing poles after one another and using this formula. But yeah, maybe this will be on the exercise sheet. I don't know. Okay, so this is that part. And yeah, the only thing remains to show is the independence of the coefficients of the lattice. And for this, well, yeah, maybe let's do it like this. Considering the derivative of this function, you get differential equation for the second derivative, which is of this form, 1 over 2 over g2. So, okay, to be precise, you don't get immediately that, you get this times the derivative of the Weierstrass-P function. But, as we will see in a second, this is no issue because the Weierstrass-P function has, the derivative of the Weierstrass-P function has very well defined zeros, and they are not in 0. So this is the crucial part. So it has some roots, but they are not in 0. So this gives us this equation actually around 0. Or alternatively, you can just, I guess, do the same thing again. So consider the explicit derivative of this above, match the coefficients, and get this expression. But now, if we plug in the lower series here, what we get is we get a relation between the coefficients by just considering the derivative of this above there and this part here. We get the following relation. Jesus. 2n to n minus 2 and a n minus 1 minus I. Okay. So what is this in the end? This gives us a way of computing the nth coefficient from all the lower coefficients. And by the explicit series expansion from above, we know that G2 is just 20 times A1, and G3 is just 28 times A2. So meaning A1 and A2 are completely determined by these constants, which depend on the lattice. But once we are given these constants, this formula is independent of the lattice. Meaning we can compute all the higher coefficients, so all the coefficients G2, n plus 2, from lower G2 and lower G3. So this is then the independence of this expression. So, and yeah, this can be proven by reduction that this is independent. So yeah, this gives us this theorem. Okay. Any questions?
And you have the times I, a n minus 1 times.
Minus, sorry.
Okay.
Yeah, this is really hard to read. Do I have this still somewhere? Yeah. Okay. These are the good thing. These are the these are the 2m plus 1. No, that's not right. These are the G2n's plus 2. So yeah, just some scalar multiples of the coefficients of the lower series. I think there should be the original G2 n plus 2, but right now I'm not completely sure. But yeah, something from which you can compute the coefficients of the lower series. Okay. Any other questions? Otherwise, I would maybe take the break here and then clean the board and then continue with the rest. Okay. Let's find out if this works.